Hello and welcome to today's webinar, Building Next-Gen Log Analytics for Scale and Performance. Today's event is brought to you by Pure Storage and Elastic. My name is David Davis of Actual Tech Media, and I'm excited to be your moderator for today's event. On the event today, you'll hear from Mr. Charles Solomon, software architect at Pure Storage, and Mr. Adam Kwan, solutions architect at Elastic. We've got a great event lined up for you today. Before I hand it over to our first presenter, I want to first remind you that we want this to be an educational event. If you're struggling with log analytics and knowing what's going on in your environment, you're not alone. This event is for you, and you'll learn about a great solution that we believe can help you to overcome those challenges. We want you to get all your questions answered, so we encourage you to use the questions box there in the GoToWebinar control panel. Charles and Adam are both standing by throughout the presentation to answer all your questions, so keep those questions coming in. We'll also be doing a dedicated Q&A session at the end of the event. Also in the GoToWebinar control panel there, you'll notice there is the Elasticsearch Solutions Brief, as well as today's slide deck in PDF. So make sure you download those resources and check them out after the event. And then finally, at the end of today's webinar, we'll be awarding one Amazon $300 gift card to a lucky attendee on this live event. If you're watching this on demand, I'm sorry the drawing has already occurred. Full prize terms and conditions can be found at events.actualtechmedia.com. And with that, I'll hand it over to our first presenter. Take it away, Adam.
Thank you. Good morning, good afternoon, good evening, depending on where you are. My name is Adam Kwan. I'm a solution architect at Elastic. In this first part of the webinar, I'm going to level set everybody by introducing the Elastic Stack and some of the solutions that we offer. We're going to focus more on the log analytics use case. At its core, Elastic is a search company. When people think about a search, they think about a search box, like what you see on Google. But there's so much more to search. Search powers many of the experiences and use cases that we live with every day. When you take a ride on Uber, Elastic is the engine that powers the Uber marketplace that connects you to the drivers. As you can imagine, this is of massive scale. We're talking about millions of users across hundreds of cities and dozens of countries. Speed is also of critical importance here. Nobody wants to wait for 5 minutes to find their driver. Yelp is another great example. When you are searching for a restaurant that's within 5 miles, opens at midnight, and accepts credit cards, Elastic is the technology that powers that search experience. Both of these are powered by search, like many, many others. Just like typing a query in the search box is a search, finding the driver nearby from a map is also a search. Zooming in onto a histogram to understand your unusual slowdown in your application is also a search. Search can be performed on not only textual data, it can also be performed on geolocation data and numbers. There are many more examples, like eBay, Dow.com, Wall Street Journal, Walmart, Sprint. All of them are leveraging the speed and scale of a really fast engine to accomplish what they need to accomplish to support their business. You might be wondering why we're talking about a search for a log analytics webinar. Well, because log analytics is also a search problem, just like many others we talked about. Finding that a relevant log entry for a specific transaction from a particular user at a certain time is a search. As a matter of fact, log analytics is the most common use case for the Elastic Stack. What differentiates Elastic from many other technologies on the market is the speed, scale, and relevance. Scale is the ability for you to ingest and interact with hundreds of terabytes and petabytes of data. Speed is the ability for you to get results super fast, even when you are working with petabytes of data. Relevance is the ability to query your data any way you want and getting the most relevant results back, whether or not you're looking at a text, numeric data, or geolocation data. In the later part of the webinar, we're going to discuss how Elastic achieves speed, scale, and relevance, especially the speed and scale aspect of it. Let me do a quick introduction of the Elastic Stack. At the core, Elastic Stack composes of Elasticsearch, Kibana, Beats, and Logstash. Elasticsearch is the heart of the stack. It allows you to store all the data you want, then perform search and analytics on top of it. Kibana is the window into the Elastic Stack. It is the UI layer, both for visualizing and exploring the data inside Elasticsearch, also for managing the whole Elastic Stack. Beats and Logstash together is the ingestion layer. Beats are lightweight shippers that sits on the edge device that picks up data and sends them to Elasticsearch. For example, FileBeat can pick up a log file from a server and send it to either Logstash or Elasticsearch. Logstash is a server-side ETL component that allows you to parse and enrich your data before you sending that into Elasticsearch. It has a rich set of input and output plugins that allow you to connect different systems together. From a deployment aspect, the Elastic Stack can be deployed on-prem or in the cloud. Here's a typical enterprise deployment architecture for Elastic Stack. As you can see, on the left side, you have Beats running on different edge devices, picking up log files, picking up metrics from your system. Those data can be sent to Elasticsearch directly, or they can go through Logstash for enrichment before sending into Elasticsearch. You can also deploy enterprise messaging systems like Kafka, Redis, and other messaging queues so that you can create that buffer system before reaching to Logstash or Elasticsearch. Again, Kibana on the right side is the console that you will use for visualizing your data, searching your data, or managing the whole Elasticsearch stack. More specifically for log analytics use case, here's typically how your processing pipeline look like. Again, typically a FileBeat is going to be picking up data either from a log file or from syslog, then send that data through Logstash for enrichment and the parsing before sending the data to Elasticsearch in the JSON format. Elasticsearch stores that data onto disk, then allows you to perform searches, visualizations, and aggregations through Kibana. As we talked about, speed and scale is of super importance for Elastic Stack. So how does Elastic achieve speed and scale and relevance? Of course, like many computer systems, Elastic achieves speed and scale through both software architecture design and hardware innovations. Elastic is distributed by design, which means you can spread both data storage and the computing power among many different nodes. As you can see on the screen, as your data grows, you simply need to add more Elasticsearch node to store and process that data. This distributed architecture allows Elastic to scale linearly as your data grows. Looking a little bit closer, Elastic achieves distribution by sharding. Each index is divided into multiple shards so that they can be distributed onto different nodes. During both ingestion and search, these nodes can work in parallel to speed up that process. So here's a high-level summary of the Elastic Stack distribution model and how it stores data onto disk. On the left side, you see the Elastic Stack. In the middle, you see different Elasticsearch nodes. On the right side, you see how Elasticsearch data node stores those data into indices, and those indices are split into shards, and shards are stored as segments onto the disk. Two of the most important processes inside Elasticsearch is ingestion or persistence and search. Let's look at both of them in a little bit more detail. From an ingestion aspect, when the data is coming in, Elasticsearch has to write all this data onto disk as fast as they can. Ingestion involves a lot of disk I/O. Data has to be written to disk as they're coming in. We could be talking about tens of thousands or millions of events per second. This can be billions of events per day. We have customers writing tens of hundreds of terabytes of data, log data per day onto a disk. So the performance of the storage system behind Elasticsearch is as important as everything else. From a search aspect, when a customer sends a search into Elasticsearch, Elasticsearch has to go through a large amount of data on disk and get the relevant result back to the customer in a really fast fashion. The search operation, just like ingestion, requires fast performant storage to support that speed. This is really a summary of how Elasticsearch, of the different resource requirements of different Elasticsearch node types. You can see some of them are more memory, CPU, or network intensive. Of great importance is the data node. Data node has very high storage requirement. As we just discussed, the data node has to write the data fast enough onto disk. It has to be able to search that data, a large amount of data very quickly and get the results back. So have a very performant and scalable storage system behind Elasticsearch is critically important. So with that, I'm going to pass on to Charles to discuss how FlashBlade can support Elastic from a scale and a speed aspect so that you can have a really scalable, large Elasticsearch deployment in an enterprise fashion. Thank you.
Thank you, Adam, for the excellent introduction to Elasticsearch and log analytics. Next, we're going to talk about FlashBlade as a data hub. FlashBlade is a scalable, modern file and object storage based on Flash technology. FlashBlade is industry's only storage system that can power such a wide range of applications, from backup, restore, to AI and analytics. Some of the large customers are ServiceNow, UC Berkeley, Broadcom, Zenuity, and so many more. The world of today comes in different forms, from backup to data warehouse to data lake and modern analytics pipeline, AI clusters. Each of them requires high throughput for a file-based storage, or simple scale-out storage, and disaggregated object storage, high performance. FlashBlade is an ideal solution. So we're going to focus more on Elastic in this data hub story. A typical open source architecture for data pipeline, specifically for log analytics pipeline, where data flows from various log sources through a collector, and then through a message queue such as Kafka. And then it's enriched, transformed, and filtered by Spark jobs with one set of indexing newer and relevant data, and send the rest to bulk storage. Further analysis are done and sent to FlashBlade for indexing, aggregate, or summary data. See the log collectors, message queue, then filter, bulk storage. It's scalable and efficient, but requires a complex infrastructure. If you look at the infrastructure and the direct attached storage model, you have to build out clusters of machines for each of the technology stack that you have. It requires a specific server configuration. It's hard to change the compute and storage ratios. In a disaggregated model with FlashBlade, you could scale out your storage separately and scale out your compute separately. So what are the advantages of a disaggregated model? In an old model, you have to build out new application silos in order to not to disturb the existing production system. This means installing software, testing, validating to ensure the system is ready to use. While with FlashBlade, because compute is disaggregated from storage, it's much more agile. You simply need to spin up new compute instances. You don't need to rebalance the data in a newly built system or validate if HDF is working. You simply spin up new applications on idle computer servers or VMs and point them to FlashBlade. It literally takes minutes to deploy. So what happens in the old model is FlashBlade when a scenario where unexpected data ingests from new data sources? It's a wholesale change in infrastructure. Where you need to increase the nodes, could probably mean buying new servers and trying to match the same configuration as before, doing some rebalance. Well, in FlashBlade, all you need to do is simply insert a new blade. That's it. The Purity software will rebalance the data automatically and deliver a linear performance boost. So what are the FlashBlade specs? You can scale up to 5 chassis, but probably about 2.5 petabytes. It's got dedicated out-of-the-box management ports. And for your linear performance, it gives you very good IOPS. It uses a single namespace. Here's a glimpse of what performance can be achieved on FlashBlade. We'll go into detail on the benchmarking in a bit. It is on par with direct attached SSD. So I want to talk about the log analytics at Pure Storage. We take pride in our support. We're very hands-on with support cases. We have a really high NPS score of over 90. How do we do this? We start by phoning home telemetry data in the form of logs. When a customer calls us with a concern, we look through this data to be able to help each of the customers. In fact, you don't even need to call us most of the time. We actually open over 70% of the cases ourselves. We do that by automatically matching fingerprints in our telemetry data and lots of times catching things before they become problems. It works very well. So where's the problem? So our dream goal is to be able to massively speed up root cause analysis, cases down to less than 30 minutes. Our customer calls in, we open a support case, and we want to find out what is the root cause of these issues. We do this analysis while the system is still scalable. It's still running in production, and there's still data pipeline active. So while we ingest and we remain scalable, we also analyze the data while it's still going on. So the pipeline powering these are typically starts about 20 petabytes of raw data. We narrow down using Spark applications, and we index only those relevant data sets in Elastic and do an analysis in Kibana. So what used to take about 30 hours is done in less than half an hour. So one of the external use case at a retailer, we solved a huge data problem growth where we replaced 5 racks of storage and compute with less than 1 rack equivalent with both hot and warm data tier. So the ingest ratio was still awesome. It gave better visibility to each workload and easier to scale for capacity and performance. The key takeaway is log analytics use data as a big data problem with ever-growing data set. A good network is key. Disaggregation provides flexible, scalable solution. So let's move on to the benchmarking of Elastic on FlashBlade. So we got together about 40 bare metal machines and set up Elastic cluster. We started with a 5-node cluster, about 6 Rally node generators, and a single FlashBlade chassis, 15 blades and 17 terabytes each. So we used the Rally benchmark tool that came with Elastic, and then we wrote our own for Logstash, which was built around JMeter. So the goal here is to find the best possible tunable parameters for the given data set. The simple configurations are just a mount point, and then in the Elasticsearch or YAML file, we just put the path data to the mount directory. That's it. In the FlashBlade, you just allocated a specific data size for the whole cluster. So the data sets we used were New York Taxi dataset that was part of the Elastic Benchmark Tool Rally, and then our own custom generated dataset on Apache Logs. For 16 terabytes of raw data for unstructured and 600 GB for structured dataset. The first measurement we looked at was bulk size scaling. Bulk inserting is a way to add multiple documents to Elasticsearch in a single request or API. This is done for performance purposes. So your opening and closing connection is usually expensive. Bulk size is independent of data analysis and cluster configuration, but a good starting point was 1K per bulk. So we saw good linear growth up to about 100K, and after that it tapered off. So that we took that as the ideal bulk size. Then we moved on to shard scaling. Shard is the fundamental unit of scaling in Elastic. Sharding allows scale out the partitioning data to smaller chunks that can be distributed across a cluster of nodes. One of the great features of Elastic is that it's designed from the ground up to be horizontally scalable, meaning that by adding more nodes to the cluster, it's possible to grow the capacity of the cluster. So in our benchmark, we got good results from 80 to 100 shards per cluster. The next was bulk index clients. It's the number of simultaneous threads or connection for bulk indexing. Good number was 10 clients. We were able to scale up and get some good results at 80 to 100. And then it tapered off as well. So we used all these three to combine them into the node scaling for Elastic. So after several iterations on each cluster size, here are the best ingestion rates for each cluster. So for a 10 node cluster, this was the best number we got. And similarly, we ran through the iterations from 10, 15, 20, and up to 40 nodes. A look at the incredible 2.5 million documents a second, which is rarely required. So see the index scalability here. When the allocated storage is almost full, generally Elastic shows a warning label in yellow in Kibana. So we did encounter this scenario when the storage is almost full. So all we did was we logged into the Purity software in FlashBlade, reassigned from 40 terabytes to 60, and then boom, within a few seconds, Elastic showed green. So that's the power of scalability of a storage. So I want to show you the FlashBlade utilization while ingesting the data. We see an average of about 3 GB per second for read and write the bandwidth. So let's go into the observations while index scaling tests. FlashBlade linearly scales at elastic nodes were scaled. This provides confidence that your Elastic cluster can grow on FlashBlade with your needs. The key tunables are bulk size, shard count, and bulk indexing clients, and these are specific to your data set. And it's important that you validate and benchmark for your valid data set. And a good shard count was about 5 shards per node. We had room to grow. The compute and memory were not optimized. We, in fact, set the memory to about 30, 31 GB per node. That's about it, as per the Elastic's recommendations. So over 3 million documents a second was a pretty high performance benchmark. This was done in one of the previous tests. So we got good results with ingestion. What about queries? So here's a graph on milliseconds on while indexing is happening, we had search query running as well. So what is the impact it has on the query performance when indexing goes on? So while indexing happened, the delta is hardly negligible. It's hardly any amount. This shows that your performance is not impacted even while indexing and indexing and searching at the same time. One of the important tests we did was to measure a performance of our FlashBlade while multiple queries are run. So we create a scenario of hot queries where typically in a dashboard scenario, you have multiple queries being run every seconds, every fraction of seconds. So while these are running, Elastic usually caches them and stores in memory, and it is serving the dashboards from memory. So while this is running, we wanted to introduce some ad hoc queries to simulate some analysis queries. And this would definitely go and hit FlashBlade to get these queries because these were not queried before. So when we hit those queries, we found that the performance was hardly affected on our hot queries. So those peaks that you see are the ad hoc queries. So while the ad hoc query ran, the hot queries impact was fairly limited. So now let's look at the FlashBlade dashboard. You see these are the peaks for the ad hoc queries because it's only the ad hoc queries that is hitting the FlashBlade this time. So we see a very high utilization, about 6 to 7 GB per second. However, in spite of the increased I/O and CPU load, the search performance is fairly consistent. This gives you a glimpse of how FlashBlade can handle the demands of ad hoc queries while yet not impacting hot queries. It meets the demands of ad hoc queries. So disaggregation allows multi-tenant implementation of Elastic, where it can scale separately. So the best practices for Elasticsearch is to determine your tunables for your data set. Set some good refresh interval. You got good results at 30 seconds, unless you need very low latency. I think 30 seconds is pretty good. Memory lock was set to true. Pre-indexing aggregations removes the overhead. And then thread pool sizing is also important for bulking. The advantages of FlashBlade is decoupling compute and storage. It provides scalability, agility, consolidation management. It reduces the number of replicas. Typically, 3 is recommended. You could go down to 1 replica as the storage layer ensures data protection. You can ingest large batch sizes for efficient I/O patterns. High storage throughput at consistent, low enough latency. This segregation enables service delivery and scaling models not possible with local drives. Thank you. We move on to the Q&A section. Here are a few questions. How large can FlashBlade be built for Elasticsearch cluster? FlashBlade can grow up to 150 blades, that is about 10 chassis. And each of the blades can hold 52 terabytes. We're looking at a total of around 9 petabytes of raw storage, and of which about 6-7 petabytes of usable space, and this is with no compression. If you add compression, you can have a lot more savings as well. And keep in mind, FlashBlade is a fast storage device. The next question, what is the performance or the peak read rate on FlashBlade during the data ingestion testing? The highest bandwidth I noticed was around 6 to 7 GB per second of bandwidth. And we really did not push harder, or could have gone much more, just to keep that into consideration that in a typical user scenario, you would have both search and ingestion going on. Another question was, what are the recommendations for configuring Elastic tiers when using FlashBlade? What tiers should be hosted by FlashBlade? FlashBlade can hold all your data tiers. It is the compute and memory that will vary for each of your hot, warm, and cold tiers. As an alternate, you could use the new frozen indices. It's part of Elastic for storing older data, and it would only require less compute and memory. And these frozen indices can still be searchable. If the size of the data grows to more than a single FlashBlade It's about 780 terabytes of raw, usable around 550 terabytes. You could add another FlashBlade. The big advantage here is that there is no cost to move your data. So for example, if you have an analytics project where you want to go deep dive into older data or do some machine learning with those older data, you could still use the same Elastic and make it searchable. You could convert your frozen indices into regular indices without moving data and simply add better compute and storage, and you have all your data available for search. This saves a lot of time and costs, and there's a huge operational benefit. And especially for deep queries and audit requirements, it's very useful.
So I do see a few questions coming in. The first one, other than the marketplace, what other use cases does Uber use Elasticsearch for? Okay, that's a great question. Other than the marketplace, Uber also use Elastic for their log analytics, also their on-call dashboarding. So basically just analyzing, customer services, different, customer calls, things like that. As a matter of fact, like we talked about, log analytics is really the most common use cases for Elastic Stack. Really a great percentage of our customers that we work with use it for log aggregation. Second question, for log analytics use case, do you always or have to use Logstash? That's another great question. No, not really. It really depends. You can perform data transformation using ingestion nodes too. So the data transformation pipeline inside of the ingestion node can use a lot of processors to basically manipulate or enrich or transform the data before writing into the index. So the ingestion processors, they are a subset of the Logstash functionality, if you will. So if that will satisfy your need, obviously, not using Logstash will simplify your architecture a little bit. I would recommend you not use Logstash if the ingestion processor meets your need. Based on my experience, majority of the transformations that you do with Logstash, you should be able to do it with Elasticsearch ingestion node. I see another question. Can you give some suggestions on how to improve ingestion performance for large log analytics use case? Yeah, I think that's another great question. There are obviously many different ways of improving that ingestion performance, but there are a few settings that can be really helpful. As we were talking about ingestion, if you remember, right, during the ingestion process, it does the flashing of the memory buffer onto disk every 1 second. So basically, it's writing that data out onto disk every single second, so that you get that near real-time experience, right? And obviously, writing it very frequently onto disk creates a lot of small segments. And those segments in the background has to be merged into larger ones, and all this consumes a lot of I/O. So if getting the most fresh data within 1 second is not that important, you can adjust that value to be to, let's say, something 30 seconds. So in that case, Elasticsearch will write a much larger buffer and creates much larger segments instead of those 1 second small ones, right? Again, that will reduce a lot of the segment writing and merge. Definitely improve the ingestion performance. Other things like you can also leverage the hard worm architecture. Basically, you can use your performant hardware as a hard node for ingestion purposes, and store read-only data onto the worm node, so that you can perform that you perform less searches, right? Also, you can, some of our customers do this. You can also, leveraging zero replica to increase that ingestion speed. What I mean by that, Elasticsearch by default has one replica, which means whenever you have a piece of a document written into Elasticsearch, it has to write the primary shard, then it has to write it into the replica shard before it's done, right? So if you define no replica, let's say in your hard phase, when data comes in, it only needs to write the data into the hard node once before it gets it back, and so reduce the amount of I/O that it has to perform. Then later on, when you move that data into warm, in your index lifecycle policy, you can define more shards so that or replicas, if you will, so that you reduce the risk of losing data, also increase the parallelism. So basically no replica for ingestion, but then when you move the data to warm, you can create more replicas as you wish. I see another question. Elastic has traditionally recommended against NFS. Is that a position changing? The reason why, in general, traditionally, we have not recommended using NFS is mostly due to the performance issue, right, for lots of NFS solutions. As we talked about, Elastic is extremely I/O intensive. If your storage is not handling the kind of I/O throughput, there's a problem with it, right? So that's mostly the reason. Another question, I saw that AWS announces the ultra warm tier to live on S3 in their managed services. Is Elastic planning on similarly using object storage for primary storage? That's a great question. Yes, so inside of Elastic, we have an internal project that's working on a portable object storage solution for something like ultra warm inside the AWS Elasticsearch service. The object-based storage is portable, meaning it can leverage, let's say, something like S3 on AWS, but at the same time, it can run on Google Object Storage in GCP or Azure. So it's not just the S3 solution. It is portable across the three major cloud providers. With that being said, I do not have a, I cannot tell a timeline, and we are working on it. I do want to say that even today, right, Elastic has hot, warm, and frozen storage. The frozen storage, honestly, is about the same performance as the ultra warm that you see inside AWS ES. I do understand, object-based storage are cheaper from a hardware aspect, right? So we bottom line is we are working on it, and I just cannot communicate a timeline for now.
All right, great webinar. Thank you so much, Charles and Adam. Excellent presentation. And thank you to Pure Storage and Elastic for supporting today's event. Charles and Adam have put their email address here on the thank you page if you have questions about their presentation or the solutions you learned about on the event today. Also, the respective websites of Pure Storage and elastic.co are on the thank you page as well. Before we go, I want to announce the winner of our Amazon $300 gift card. That's going to Jeremy Spring of Missouri. Congratulations, Jeremy Spring of Missouri. If you didn't win a gift card today, sorry, we've got more events coming up at events.actualtechmedia.com. And before you go, I want to remind you to download the 2 handouts that are available there in your handouts tab. There's the Elastic Solutions Brief and the entire slide deck from today's presentation in PDF. Go ahead and download those now. You won't have access to those after the event. Again, thank you so much to our presenters And thank you to our audience for joining us. I hope you learned a lot and have a great day. I'll see you next time. Bye-bye.